All right, just one more minute and we'll get started. Okay. All right, I'm going to preface this by I had the beginnings of a migraine this morning, and so I took my cocktail of drugs, and so I feel a little wonky. So I like caught myself, like I felt like I was slurring my speech, and I was like, I'm not drunk. I'm just medicated in a very prescription way. So there you go. All right, we are starting gases today. And let me get rid of some of these things since we're going to add it up there. So, we talked about solutions. We obviously talked about solids in chapter 4 and 3. And we talked about solutions last chapter. We sort of talked about pure liquids in chapter 2 or 3, where we said that we could use density to convert between volume and grams. We don't focus in on that a whole lot. If we ever do, I'll, walk you through the type of problem. But now we need to talk about gases, because we have chemicals that come in all of these different states, and we need to be able to take those and convert them into a usable form. So when we talk about the properties of an individual gas, it's interesting, but it's almost a little bit more physics than chemistry, like how a gas behaves. What we want to know is how we can utilize that behavior to determine how much of that gas there is and how it's going to react with something. Because chemistry implies that we're talking about a chemical reaction. We want to break bonds and form new ones, okay? So a big part of this is going to be determining the moles of gas that we have, and then from the moles of gas, looking at how does that affect the pressure in the end, or how does that affect the volume of the gas in the end. Okay, so I am going to be jumping around a little bit in the slides just because every year I tweak a little bit and say, maybe it makes more sense to do this part first. And so I like how I did it last class. We're going to do it the same way there. So just try to keep in mind that it's not always going to be the next slide. So I'll say, okay, 2 or 3 slides ahead, that kind of thing. All right, so I'm going to start with the simulation actually. And we are going to look at how a gas behaves with all of its different properties. So the properties of gases that define a gas are its pressure, which we abbreviate P, and that's units of atmospheres is what we are going to kind of have our standard unit. The volume, V, and that's going to be in liters. The moles, N, because we can't use M because that's molality. Why don't we use MOL? Because we want it to be one letter. So I don't know, N is the next letter or something. Number of moles, maybe. Anyway, that's in moles. And then temperature. That's going to be T, but it's going to be in Kelvin. A couple important unit conversions. Obviously, if you're in grams, you guys know how to get to moles. If you're in milliliters or something, you can get to liters. The other pressure unit that you'll see frequently is torr. So we'll show you some more details on that. This is in your exam equation sheet, but it's 760 torr per atmosphere. So if you have to switch from torr to atmosphere, you can utilize that. The other name for torr is millimeters mercury, mmHg. It's just a different name. They're the same thing. And then the other conversion you'll need is Kelvin is Celsius plus 273. Technically it's 273.15. Usually 273 is adequate, but we'll put that on there. Okay, so all of these properties together are interrelated in how we define a gas. So unlike grams to moles, which is just one simple conversion, if we wanted to find moles of a gas, we would actually have to know the pressure, the volume, and the temperature. It would take a lot of information in order to determine that. So what I want to start with is looking at each of these properties and how they're interrelated. When the experiments that originally were done on gas properties were done, they always isolated two properties and kept everything else the same. So for instance, we're going to look, let's see, which one did I do first? We're going to look at how volume and volume and pressure are related. I'm going to do these in the order that they're in the notes. So let me look at that first. Nope, it was moles and pressure. Okay, so we're going to look at moles and pressure, then volume and pressure, and then those ones I can't do in the simulation, or at least not in that simulation. So then we'll also probably do temperature and pressure, even though it's not in the notes. So I want to look at how changing these variables changes one of the others. And ultimately, I'm trying to get to a point, and like I said, this is how it was done when the original experiments were done. They did individual relationships, and then they put those all together. So we're eventually going to, and if you took high school chemistry, you probably know where I'm going with this. We're going to take all of these things together and create one single equation that relates all of those properties. But in order to do that, we have to understand the relationship between each two sets in order to be able to write an equation to describe the whole thing. Okay? All right. So eyes up on the simulator. I'm going to add some gas. It's kind of fun. You can play with it if you want on your own. You're going to pump a little bit of gas in there. And as you can see, it's separating out. They're not attached to each other. They're not interacting with each other. They're kind of just aimlessly bumping around the container, okay? This is what gases look like. They do not have a definite shape. The volume is just the volume of the container that they're in, and they're not restricted with each other. A liquid and a solid, they have interactions that hold them together, which is why they have a shape. Or a specific volume, okay? So if we want to look at number of moles and pressure, let's pay attention to this pressure gauge here. It says that our pressure is 5.8 atmospheres. Before we do anything else, let's talk about what we mean by pressure. In the notes, it says that pressure is force over area. That's like a very physics definition. So if I take the palm of my hand and I press on the table with a certain amount of force, the pressure would be the force I'm pressing with over the area of the palm of my hand, okay? If I take a pen and I press that same amount of force, but now the area is much, much smaller, the pressure there is way higher, okay? Because it's force over area. This is the whole idea of like a stiletto heel versus, I'm sure all you guys know what I'm talking about, a stiletto heel versus like a chunky heel, right? You can walk on grass just fine in a chunky heel and nothing's gonna happen, but if you try to walk on grass in a stiletto heel, it's gonna go right into the mud, okay? Because there's a lot of pressure because the area is so small. And I'll pass this around while I'm thinking about it. Okay, so when we talk about gas particles and pressure, it's still force over area. It's just not the force of a whole thing. It's the force of individual particles, and the area that they're pressing on is the size of the container. Okay, so let me say that one more time in a different way. The pressure of a gas is how often those particles that are bumping around hit the sides of the container. When they hit the container, they apply a pressure, and that pressure is applied over a particular area of the container itself. So if I add more particles, so I'm gonna pump the little thing one more time. I want you to see what it does to the pressure, but I also want you to think conceptually why that's the case. I'm gonna add more. Okay, so the pressure went up, right? So if we increase the number of moles, we're going to increase the pressure as well. Okay, so why did the pressure increase? Conceptually, why did the pressure increase? Is each particle hitting the container more often? No. There are more particles to be hitting the sides of the container. So like if you had 10 in there to start, okay, maybe they hit, once a second or something. It's more than that. But let's pretend it's once a second and there's 10 of them. Then you add 20, they're still hitting once a second, but there's 20 of them hitting once a second. So the more the particles hit the sides of the container, the more pressure there is. It doesn't matter if that's because the particle itself hits it more or there's more particles hitting. Okay, so that's why we see an increase in pressure. We say that these are directly proportional, meaning if one goes up, the other one has to go up. And the way we describe this mathematically is to say pressure over N is equal to a constant. The constant itself doesn't actually matter what that number is. We just are saying if this one goes up, that one's going to have to go up in order for it to remain a particular ratio. So like if this was 1 and this was 2, and then N goes up to 10, P is going to have to go up to 20, right? If one goes up, the other one's going to have to go up. So you'll see that anytime things are directly proportional, you're going to see them like on the same side of an equation, one on the numerator, one on the denominator. Okay, let's do volume. Next, volume and pressure. So I'm going to leave the container like it is, but I'm going to make I'm going to leave the number of gas particles like it is, but I'm going to make the container bigger. Before I do that, I want you guys to think of that definition of pressure, that it is how often the particles hit the sides of the container, and guess, is the pressure going to go up or down when I make the container bigger? Okay, so keep it in your head, but just take a guess. And watch the pressure gauge as I drag this guy out. Okay, so I made the volume bigger. I'm going to have to look for another marker. But the pressure went down. So the particles didn't change. They're still moving at the same rate. There's still the same number of them. But because it's harder to get from one wall to another now, because it's a bigger container, it's registering as lower pressure. Because now they have to travel all the way across if they want to hit the sides of a container. They're just not hitting it as frequently. Okay? So this chapter is a decent mix of concept and math. You guys have to be able to understand why a change in volume affects pressure, But then you're also going to have to be able to do calculations that relate volume and pressure. Every time I think that's a question when you're stretching. You're in a very stretchy mood this week. I'm like, question, no. Okay, last one we're going to do on here is temperature and pressure. So I'm going to leave everything as is, same number of particles, same volume. All I'm going to do is increase the temperature. Okay? Temperature is a measure of kinetic energy, particularly temperature in Kelvin. It really just tells us how fast particles will move. So if you think of ice, those particles are really cold. They don't move, at least to you, they don't look like they're moving at all. They're moving very, very slowly. They're just kind of vibrating back and forth. When you get to a liquid, they're moving fast enough that it's visible. You can see that they can move freely. And when you get to a gas, they're moving so quickly that they're bouncing off each other and they're separating from each other so much that you don't even see them. Okay? All right. So if we increase that temperature even more and they move faster, take a minute and take a guess of how that's going to affect the pressure. All right, here we go. So I'm going to heat this up, and I'm going to be a little bit dramatic just so it's clear on what's happening. All right, 1400 Kelvin. That's probably pretty good. Okay, so what are the particles doing? Moving faster, which means they're hitting the sides of the container more frequently, which is why we see an increase in pressure. Okay, so these are relationships that are not just, oh, I need to know that pressure and temperature are directly related. You can remember that by actually thinking through what is that definition of pressure and how does it going to relate to things. How is it going to relate to how the other one responds? Okay, so this one is also directly proportional. So we would write this as P over T equals a constant as well. And then for this one, they're inversely related. And the way we write that is we write them next to each other is equal to a constant. This is because, like, if this one was 10 and this one was 20, if I increase the pressure to 20, that means this one has to go down to 10. If one goes up, the other one has to go down. That's the only way for them to stay constant. Okay? So, little lesson on what do we mean mathematically when we say they're inversely proportional or directly proportional. Okay, so we're going to switch off of this one. I'm going to point out where this is the slide that talks about the first one, N and P. Same thing we just did. This is the slide that talks about P and V. Same thing we just did. It sets up the equation PV equals a constant. And we're going to come back to this practice problem, probably not even until Friday, and deal with how do we use that relationship to account for a change and predict, in this case, what the new volume would look like or what the new pressure would look like. Okay, one that's not in the simulation, or at least not in that simulation, is volume and temperature. Okay, so volume and temperature. And anytime we're talking about two things, we have to hold the other things constant, or else it would all get mixed up and confused. So N and P, we were holding V and T constant. When we did V and P, we were holding N and T constant. And when we did T and P, we were holding N and V constant. Okay? Now, with V and T, as well as with, I think it's N and V next, we are going to be holding pressure and temperature constant, pressure and moles constant, and then we're going to be holding pressure and temperature constant. So when we hold pressure constant, it's a little bit different because What we're really saying is that the container that the gas is in is flexible and will always flex and change its shape in order to maintain a constant pressure. So it ends up matching the pressure from the gases that are pushing on the outside. But the key point is that this one has to have a flexible container in order to maintain constant pressure. So if you're ever doing a problem where it says, you know, in a rigid container, they mean volume is constant, unless they change the volume. They do not mean that pressure is constant, okay? A rigid container does not ever have a constant pressure. It's dependent completely on the gas inside. A balloon, there's the gas inside, but it's going to push against the walls and stretch them out. It's going to change the volume in order to have a constant pressure. Okay, so volume and temperature, you guys may have seen this. It's kind of a fun little experiment you can do at home. So you go outside on a warm day, you fill a balloon, tie it off, so you keep the number of moles the same. The pressure's the same because it's a flexible container. Then you take it inside and stick it in the freezer or put it in an ice bath or something, and you will see the volume of it get smaller. The reason is because the particles start to move more slowly, so they're not bouncing around, they're not hitting the sides of the container as frequently, and then that volume starts to decrease in order to keep the pressure the same. So like if they're hitting the sides of the container, I don't know, 100 times every second, then they cool down, and now maybe they're starting to only hit 50 times or 10 times a second. Then the volume, the container has to get smaller in order to keep them hitting 100 times a second so that they can get across even though they're going slower. Okay, so when we increase, there we go, when we decrease the temperature, the volume also decreases. So again, directly proportional. So we would write it similar to this one. V over T equals a constant. And then the last one is N and V. This one's pretty easy to understand. You have a balloon, you blow a certain number of moles of gas into it, you hold it there, it has a particular volume. What do you think is going to happen to the volume if you blow more moles of gas in? It gets bigger, right? Because it's trying to maintain constant pressure. And so the way it maintains that pressure is by getting bigger so that those additional moles of gas have to travel farther and therefore hit the sides of the container the same as they did before. Okay, so if you increase N, V will also increase. So yet another directly proportional relationship. So if I have room for this. So V over N is a constant. So the cool thing is all of these laws, all of these relationships can be treated completely individually. We can say, hey, I have this gas, it has a particular volume, particular number of moles. I add more moles of gas, what happens to the volume? And you can calculate that. Or you can do that with pressure and volume. I have a pressure and a volume, what's the new volume that happens? We have a lot of time. Why don't you guys go ahead and take a shot at this one? Now, I would like you to go ahead and stick to liters, atmospheres, moles, Kelvin for all of the problems. There are ones, if you get in there and see, oh, I don't have to actually change that, that's fine, but don't do that until you are sure of that. we get a new volume? Somebody shout it out. Be brave. I swear someone got it. You're just being too shy. Okay, so I am going to go ahead and put this in liters. There's my volume 2. 1.24 times 0.651 divided by 0.412. So V2 is 1.96 liters. Okay. So that volume, I'm just going to double check it conceptually to make sure the math was done right. That volume is significantly bigger, which makes sense because the pressure decreased. So I increased the volume, and that made the pressure go down because the particles had to travel further, so they weren't hitting the sides of the container as much. Now, why was I able to set up this relationship? Because pressure times volume is equal to a constant. So anytime I change the pressure and volume, it's going to be the same as another time when I change the pressure and volume. So if you have one scenario and another, you can equate them. We don't have to actually know what the constant is. We just need to know that you can equate them. Yep.
How did you get
Did I get it wrong?
0.651?
Oh, because it's 65 milliliters. So 65 it should be 0.0651, right? Yeah. Which changes our answer to what?
0.996.
Whoa, wait. That's way too small, though. Okay, hang on. Oh, I guess I would have been comparing it to the wrong thing. Okay, yeah, that's fine. So it's still larger. It's just larger by a different way. Thank you. Oh, and I forgot a 4 there. Sorry, I'm just double checking myself now again. Okay, good. Okay, so still larger container, lower pressure. Okay? Okay, so when we had all of these individual relationships, the kind of next step was to put them all together. So like I said, we're going to come back to these individual problems, but I want to show it to you all together first. So here's a few of those individual relationships. And what was done was those were then summarized into what we call the ideal gas law. So this is what I meant about if you had chemistry in high school, you know, these started to look familiar. This is kind of the big takeaway that we teach in gases in high school is the ideal gas law. PV equals nRT. So pressure in atmospheres times volume in liters is equal to the number of moles times the gas law constant, which is this one, 0.08206, times T, temperature in Kelvin. And now we can apply this to an individual setting, not where there's just a change happening, but where we have all of 3 of the 4 variables and we can determine the other one. And this is really important because sometimes, yeah, we're changing the volume and we want to know how the pressure changes, but sometimes we just want to measure what the volume and temperature and pressure is so that we can determine the moles. Okay, so that's when this equation is going to become particularly useful. The gas law constant is on the exam equation sheet. Let me show it to you real quick. Be careful that you realize that it's that R. So the gas constant in different units is useful for something else. So this is actually the same constant. It's just now in joules per mole Kelvin. That's not what we want to use. We want to use liter atmospheres. Okay, so make sure you're using the correct constant. And then we also have the PV equals nRT equation down there. I'll show you when this version of it is going to become helpful. But we have the PV equals nRT. I feel confident you're going to know these by the end of the chapter. It's just like it's to make you feel better in case you clam up during the exam. The conversion between millimeters of mercury and torr to atmospheres is there as well. Don't get confused. Remember, millimeters of mercury and torr are the same thing, just a different name. The guy's name was Torricelli. He measured things using mercury, heights of mercury in millimeters. And then later somebody was like, oh, we should give him credit. So they changed it to torr, and now we use both of them. Okay, so let's do one practice problem with the ideal gas law. Not that one. And then we'll go back and talk about pressure measurements, how those are done in the atmosphere, and also how they're done in an experimental setting. So take a minute using that PV equals nRT to solve this problem. Okay, so with a problem like this, it's best to go ahead and like make a list of the variables, make sure they're in the correct units, then go ahead and plug them into the equation. Okay, so pressure was the only one you had to convert. If, you know, I might just write it like, okay, temperature, that's the thing I don't know, moles, volume, pressure. And then I would double check the units and say, okay, I need to convert the pressure. If you want to write it out as a nice little list, that can be useful too. Okay. I love the units of constants. It took me a long time to get to that point, but I really love them because they are basically telling you how to do the equation. That's a conversation for another day, but they're certainly telling you how to, which units you have to have them in. So just by looking at the units of the constant, that's a reminder of the units that all your variables have to be in. So liters, atmospheres, moles, Kelvin, that's on the exam equation sheet, reminds you of all of that. So that's your reminder, switch to atmospheres. Okay, so now we were able to figure out the temperature of a gas, knowing all of those other variables, simply through this ideal gas law. And what's really cool is that this ideal gas law is going to tell us the relationship not only between all four variables, but these relationships, instead of memorizing them, we're going to be able to pull them out of the ideal gas law. So it's like we memorize or learn one thing, and then we can pick out all the little bits and pieces that we need. So let me show you what I mean by that, and then we'll apply it on Friday. So if I rearrange the ideal gas law to look like this, so the constant is NT over PV. Now, if I pick any two variables that I care about, let's say, I don't know, T and V. So that would have been Charles' law, the one where we took the balloon and cooled it down. I can just say, zoom in here, I can say N was constant. We weren't putting in any more gas. P was constant because we were using a flexible container. And now my equation becomes T over V, and then I set that equal to T2 over V2. So I basically use the ideal gas law to create one of those individual relationships where I have a change. Now, the ideal gas law is what's required when you're not changing anything, you just have a static situation. You have to know all of the variables to find another one. But if there's a change occurring, that's where you're going to have these 1 and 2, and you can create those equations from the ideal gas law. So up here, there we go. That's this one. So I had R equals, now it probably was flipped, I think. Yeah, I think it was flipped. Do I have it that way in the exam equation sheet? I think I have it the other way around. PV over NT. Yeah, it's not wrong. It's just going to be the wrong R. So scratch this out in your thing and put PV over NT equals R. You'll get the same answer, but this one makes a whole lot more sense. Now I got to go in and make sure to change that for next year. Okay, so again, I would pull out V and T, and I would get V over T equals V2 over T2, or 1 and 2. Okay, and that's how I would do a problem like this, because you're not going to be given each of these individual equations. You are going to develop them, I guess, if you want to call it, or pull them out of that one equation, which is why I have on the exam equation sheet, I have PV equals nRT, but then I also have it written in that other form, R equals PV over NT. Okay. All right, we'll do quite a few of these individual problems. We'll do some stoichiometry problems on Friday. But the last thing I want to talk about today that we kind of skipped over is how pressure gets measured both in atmospheric settings as well as in experimental settings. And these basic ideas are still how we do it. We just do it a little bit more advanced, but the basic principles still apply. So a barometer is how we measure atmospheric pressure. You've probably heard that, like the barometric pressure is, you know, such and such dropping today, usually is an indicator of like a front, like storm coming through. And that pressure is measured, this is where this whole millimeters of mercury thing started. Mercury is really heavy, it's one of the heaviest liquids. And so we use it so that our little tower can be, you know, 760 millimeters instead of like 5 meters or something, okay? So what we do here is the container is open to the atmosphere, this container of mercury, and there's gas particles in the air bouncing around, hitting things. They hit the mercury and apply a pressure, they apply a force. Now if there's lots of particles, let's say sea level, there's lots of particles, maybe it's a warm day, and they're hitting that container, they're going to push the mercury down, which will push it up this tube, okay? So normal conditions, atmospheric pressure at sea level is 760 millimeters going up this tube. And that's why we set that to 1 atmosphere. Now if you go take this up to the top of a mountain, there's less particles. So the further you get away from the center of gravity of the Earth, the less well held any gas particles are to the Earth, and so it's thinner. There's less particles of gas up there. This is why you get like sick when you go to the mountains, because there's not enough oxygen. That's why I get sick. Maybe you don't. So now there's less particles hitting this mercury. So there's still some, but less. And so this mercury gets pushed down, but maybe not as high. And so maybe it rises to like 740 or something, okay? So that's how they measured the atmospheric pressure. And like I said, that can change with like weather patterns and stuff as well. I'm not done. I got 5 minutes. Chill out. Okay, the second one is measuring gas in an experimental setting. I scratched that out because that, I don't know where that came from, and it was confusing. All right, so you've got a closed system over here where you have a gas in, like, either that was just produced in an experiment, whatever. You've got a gas in a system here. Then you have this tube system that again has mercury in it, and you've got the atmospheric pressure. So let's say that the atmospheric pressure is normal, like 760 millimeters of mercury. And if, let's kind of go back and say, what if the gas was also 760 millimeters? They would both be pushing on the two sides of mercury equally, and so you would actually see the mercury at the same level. Okay, so that would be if both of them were 760 millimeters. Whichever one is higher, though, is going to push down harder on its side of mercury. So this gas over here is pushing down more, and it's rising on this side. That means this guy has a higher pressure. The amount by which it's higher is determined by the difference in the two levels. So here the difference is 100, and we know it's higher on the gas side, so that would mean that this one must be 860 millimeters of mercury. If it was the other direction, we would know that the atmospheric pressure was higher, and therefore we would subtract the 100 to find the gas. Okay, so you'll do a couple problems like that to get familiar with it in the homework and as you're going through the textbook. Okay, all right, so I think that we'll stop there, and we'll do lots of math on Friday. Yeah, that will be good. And then this will be Monday. Hi. Oh, just that number? That's a constant. So that's from your exam equation sheet. It's also in the notes that we had.
Okay.
Yep. Yes, yes.
Did you get everything I sent?
Yes,
last
I
night?
emailed you this morning.
All right, I didn't check. my
That's
emails
okay.
Yet.
I know. That's some people are like night emailers. I emailed first thing in the morning. So just read it. Let me know if you have questions.
Okay.
Yes.
So I understand how to get in all of these. How do I get T?
So you're gonna have to like do the algebra, which is divide both sides by 2.1, and then divide so that it cancels, and then divide both sides by 0.08206. So that would be. Well, this you need to change to atmospheres as well.
Okay.
So you left that in Tor, so put the 1.2 there.
I see.
So 1.2 times 35, then divided by 2.1, and then divided by 0.08206.
So this here doesn't.
The units don't matter, they will cancel out with the units you have. If you rearranged all of these, you'll see that the atmospheres will cancel out with atmospheres, liters will cancel out, and then you'll just be left with the Kelvin, which
Okay.
is what you want.
Okay.
Yeah.
Thank you.
Mm-hmm. Hi.
So you think it'd be better if I drop it instead of?
I'm not gonna say I think it would be
Right, right,
better.
right. So, like-
But like, if you want, we can go through like what your current scores are. Like somebody else asked me to do this, they said like, how likely is it for me to get a C? I'm like, well, you would have to get a 65, wait, that wasn't you, was it?
No, that wasn't me.
No, okay. You'd have to get a 65 on this, on the rest of the test, and you know, like whatever, to get the barely into the C range. So we can go through that and figure out what that would be, and you can decide, like, do I think that's achievable?
Okay.
But then there's this other factor of like, some people can't drop classes because if they go beyond, I think it's 12 credits is full time. So like if you're at 15 or 14 and you drop the class, then now you're not a full-time student, then that affects like federal funding and stuff,
Yeah.
which is why I'm like, consider it, but don't do anything before you talk to your family and your advisors and stuff.
Okay.
So if you want me to break down your grades, just send me a quick email back
Okay.
and I'll like do the grade breakdown for you so you can see how realistic
Okay.
it is. Does that sound good?
Alright. Yeah, thank you.
Okay, yep. Hello.
Hi.
How's it going?
I was listening to you earlier and I missed the Google Meet part and I was like, wait, what room Google Meet's
Oh, did you?
right?
Why
Tomorrow.
did I, yeah.
After
Oh, tomorrow. Was it to, what was it to talk about? Your grade?
No, I'm just so lost.
You're just still, you
Uh,
think you're lost?
No, I am.
Okay,
On chapter
so why
5.
did I not just suggest 12? Is that, did you say you have a job interview?
Yes.
Oh,
That's
okay,
why.
because we normally meet 12 after
Yeah,
whatever.
But I also have
Okay.
a class, so I'm already skipping that class to go to my job interview. It's fine now.
Do you normally skip that class when you come and see me at 12, like
no,
on
I've
Monday?
I've never come to see you at 12.
Yeah, you have on Monday, didn't you? I swear we did that. I can't tell if I'm confusing the time or confusing you with someone else.
Probably me with someone else because at 12 I don't have any classes, so it's my nap time. On Mondays. So
You're like,
definitely
I know I didn't see you.
I was not.
Because I could have confused the time though. Anyway, that's fine. I love that you have a nap time. Mine's like 2 o'clock. I don't always get it, but like I gotta get the nap at 2 o'clock before my kids come home at 3.
I have rehearsal at 5 and that's tiring.
Yeah.
So I always take a nap at 12.
Yeah,
on
I love it.
Mondays,
You
so,
know
like,
yourself. That's
I
fine.
know.
Yeah, so we can do, here's the options.
Mhm.
We can do Google Meet if 12 o'clock doesn't work.
Mhm.
You could skip your nap on Friday or push your nap on Friday and we can meet at 12
Mhm.
on Friday if you'd rather do in person. So, because I'm just not on campus on Tuesdays and Thursdays.
2 seconds.
Also, I will probably be covered in dirt if we do Google Meet because I'll be in the garden and then I'll just come in and do the meeting with you. But I'm fine with that.
Actually, can we just do tomorrow for Google Meets?
Yeah. What time?
You just said after 9:30. I can do literally anytime. So maybe
Okay,
like-
let's just do 9:30 then.
Okay.
Does that sound good? And last name, remind me.
Rodriguez.
All right, I will just send you a link when I sit down. I'll just create one, or maybe I can do it right now. But no, I probably don't have your email in front of me. I'll just send you a link, but just plan on 9:30.
Okay.
Sound good?
It's generally just chapter 5. I'm so
Okay.
so lost.
Well, whatever you can do to like bring in specific topics, like say, I have no idea what you were talking about with molarity.
Well, I can just.
Or,
It's really like the practice problems,
Oh, okay.
even when you were doing them. So maybe I'll just like show you which ones I was having trouble.
yeah, perfect. That's perfect.
Thank you. I'll
Yep.
see you tomorrow.
No problem. Yep.